so much, Ali, for thank you so much, Ali, for the introduction. Um, Very delighted to be here today to present this topic of transient stability of grid-forming inverters. And I'm hoping that you'll see a few topics and concepts that are useful for our energy transition using grid-forming inverters. To start with a very brief overview of what I'm going to talk about today, I'll be going through a very brief introduction. I'm expecting that most people today here are familiar with the concept of grid-forming inverters and already know what exactly they are, but a very brief introduction into them. And then I will dive into the concept of transient stability, particularly with a focus on current limited grid-forming inverters, and we'll see why. And particularly, we'll focus on transient stability of Q prioritized grid-forming inverters, and we'll have a look at also transient stability of a pair of grid-forming and grid-following inverters, and finally some enhancing controls. We'll see how we can improve stability based on what we'll see. I am guessing that most of you have seen this, and courtesy of UNIFI website, very interesting figure that shows what's happening, what has been happening in the past, what's the current trend, and what's going to be our future. Very interesting graph. I like it very much. Previously, obviously, we had dominantly synchronous generators in our grid, and now we are having more of grid-following inverters in the mix. Less of synchronous generators, and they are being retired around the world. And the idea is that we will be replacing them almost all, hopefully, or as many as we can, with inverter-based technologies. But what we're doing currently mainly is grid-following inverters. Certain countries in the world, they're installing grid-forming inverters as well, particularly in Australia. We've been installing grid-forming inverters since I think 2017 or so, and recently being accelerated with a number of initiatives that we have actually been looking into through our Australian Renewable Energy Agency, which is funding a number of grid-forming inverters to come to the grid. So what we are seeing here is going to be probably the norm in years to come. In probably 10 years from now, the majority of power systems around the world will be seeing a lot of grid-forming inverters in the mix. But why are they important? Well, I like this graph very much. This is a graph from the Australian Energy Market Operator in a document that was published back in 2021. They were talking about expectations that we might have from grid-forming inverters and what they are from inverters actually, not only grid-forming, from inverters and what we are expecting them to do. So while we are retiring synchronous generators, we are expecting these new inverter-based resources to be able to first operate in weak parts of the network. That's a big challenge that we've got, particularly in Australia. Australia has a very strange grid, a very long grid, which is also very weak in different areas. So we expect our IBRs to be able to operate there. We would like them to support system security and make sure that they are enabling the system to operate normally in terms of system strength, voltage support, inertial support, frequency control. We expect them to be able to operate in islanded operation. And ideally, we want them to also be able to help us with system restart. Currently, system restart capabilities are dominantly offered by synchronous generators. So we expect the IBRs that are going to be replacing our synchronous generators, we're expecting them to offer all of these services. But what do we have at the moment? Well, the majority of IBRs that we've got at the moment are grid-following control, based on grid-following control, and they are unable to provide all of these services that we want IBRs to provide. Particularly, they've got a difficult time being connected to weak grids. They do not really support system strength, voltage control, frequency control. Well, to some extent they can, but they're not perfect. Islanded operation alone, they cannot. and also the idea of system restart is also not possible. But grid forming inverters, they can actually have some sort of internal reference for the voltage, and they can provide quite a lot of these services that we would like them to provide. You might have seen this graph before, or variations of this, where a grid following inverter is dominantly based on a PLL, which would look at the point of connection voltage and will inject real and reactive power to the grid, and you can look at it as a current source. Well, of course, you can expect a grid following inverter to inject some reactive power for you to help with voltage control. Yes, that's a possibility, but it's got certain limitations. On the other hand, a grid forming inverter, they can look at it as a voltage source. It does not really require the voltage at the point of connection for synchronization. It gets synchronized with the grid through power synchronization, and I'll talk about that in a minute. But it is not relying on that PLL, and it can provide all the services that I was talking about. So the trend is actually towards grid forming inverters, and we are hoping to have more and more of these grid forming inverters in our grid. Well, there is a very large number of methodologies for control of grid forming inverters. I've categorized them into three main categories here: droop-based control, synchronous machine-based control, and other approaches. And well, there might be more, but these are the ones that I could come up with in terms of categories that I was looking into. And a number of them are, of course, much more utilized and well accepted. Frequency droop is very, very well accepted, and VSG also extremely well established and utilized in various commercial products as well. And these are the two variations of VSG that, well, probably more interesting is the compensated one. This is a strategy that we proposed 2 years ago, which is based on VSG, but provides a little bit better performance. But mainly these two, the droop and the VSG, are, well, very well known, and I believe most commercial products are either using exactly them or a variation of them. Having said that, we need to acknowledge there are other variations such as VOC or other approaches that people might use. But for this presentation, I'll be mainly focusing on frequency droop or VSG type controller. Well, what is that? What is that VSG or droop? Well, the way it operates is that you typically want to control the voltage at the point of connection of your grid forming inverter in order to be able to exchange power with the grid and provide the services that you require to the grid. Typically, you've got a current controller. That would be the first layer of your system, the first layer of the control system that controls the current of this inverter. The second layer that you typically have is a voltage controller that controls the voltage at the point of connection. This voltage controller gives references for your internal current loop, and it receives some references from another loop for the voltage. So it receives essentially the frequency and the references for D and Q component of the voltage at the point of connection. Now, there is a primary control level that will provide these references for you. So the primary control level is responsible for controlling the real and reactive power of your inverter. It will provide the references for the voltage controller. It will provide the frequency with which this system will operate. And at the same time, it is responsible for controlling real and reactive power at a given reference. Of course, you've got a power calculator that you calculate the power at the point of connection, and this is the P and Q of the inverter. So this is a generic structure. I'm not suggesting that every single grid forming inverter must operate with this, but this is pretty well established in the literature. And this is the structure that I'll be using in this presentation for the concepts that we are going through. This P0 and Q0, which are the references for your real and reactive power, are given to you by other control layers. Typically, a governor or an AVR can be responsible for providing you with this P0 and Q0, but we're not really focused on these control layers for this presentation. We are mainly looking into this structure, and we want to understand what happens to this structure when we are subjecting our grid forming inverter into a fault or different transients in a power system. A closer look at the primary control level, like I said, we are typically receiving real and reactive power set points, and we calculate the real and reactive power of the inverter in order to provide VD and VQ for the voltage control loop and the frequency. So typically what we've got in that are two separate loops. Most of the time we treat the system as a decoupled system. When I say decoupled system, we assume that we are operating in a transmission network, for example, in which we've got a very inductive grid. That means our reactive power is proportional to the magnitude of the voltage, and our real power is proportional to frequency. So we can have two separate CISO loops, single input, single output loops. One of them is called RPC, or reactive power control loop, and then one of them is APC, or active power control loop. Like I said, our reactive power is proportional to magnitude of the voltage, so you can have a loop around reactive power and magnitude of the voltage. Typically, you force your VQ to 0, and you get VD through a CISO loop here. And also, you have this proportional or linear relationship sometimes between your real power and your frequency, and you can get the frequency that you require for your operation. So this is a typical way. Having said that, if you've got a system which is not really inductive, and it is something in between, you've got an XR ratio of 2, 3, 1, so it means that you're not really decoupled, even though this can work, but it's not perfect. It will give you a lot of coupling, and there are certain ways of decouple the system in that way. But for the sake of this presentation, we assume that we've got a good decoupling between our real and reactive power, and we can control them independently using these two loops that we've got. Typically, what we do in a group control, if you want to have an RPC or reactive power control, it's as simple as putting a proportional gain. Very simple. So this is the AVR I was talking about, which gives us the reference for the reactive power. It could be RPC with like a group with a low pass filter. So that's a possibility as well. Again, the AVR will give us a set point for power. We calculate the power of the inverter, and using an RPC with a low pass filter, we can come up with the magnitude of the voltage, or the component of the voltage. It could be realized with a VSG type controller, but less common. For the active power controller, very similar. If it is a group control, we do have, again, just a gain, or it could be a gain with a low pass filter. We would use a governor there to give us a set point for power. And this could also be realized by a VSG. This is very common to actually have a VSG implemented into the active power loop. What VSG is essentially emulating the shaft dynamics of a synchronous generator. So essentially, you're writing the swing equation of a synchronous generator there, and you are passing the error in your real power to that, and it will give you the frequency of the system that you're connected to. Essentially, it helps you to get synchronized with the grid without the use of a PLL. There are certain variations, like I said, CG-VSG, which is compensated generalized VSG control, or generalized VSG control. What they are, without going into the details of them, essentially this GVSG is very, very similar to VSG, except there's a lead lag control there as well. So if A and B in this lead lag control are the same, obviously it becomes exactly identical to the VSG. But if A and B are not the same, then you can exploit certain advantages here and provide better performance, particularly less oscillations when you're in a stronger grid, because typically VSG-based control might give you a hard time when you're operating in a very strong grid. CG-VSG is also another variation that can provide even better performance, but again, I'm not going to go through the details of these. If you're interested in these two structures, you can search for a paper that we published. I probably should have put that paper here But if you search for compensated generalized virtual synchronous generator, and my name probably will come up, and you can have a look at that structure. With this introduction, let's have a look at transient stability of grid-forming inverters and what happens when we subject this particular structure, control structure, to fault and how it might behave. But before going there, a very, very short recap of what is transient stability. Transient stability essentially determines whether your system is able to recover to a stable operating point after large disturbance in the system. What is a large disturbance? It could be fault, it could be voltage sag, or different types of larger disturbances that can happen in the grid, like line tripping. And typically, large signal or transient stability is in front of your small signal stability analysis. And the small signal stability analysis tells you whether your system can stably operate around a given operating point. So you typically have a linearized model of the system and say, okay, if I'm operating at this particular point, can I maintain my stability or not? And typically that is done through eigenvalue analysis and making sure that all of the eigenvalues are at the left-hand side. But transient stability tells you that if you're operating at this operating point number one and something big happens in your network, a fault, line tripping, generator tripping, things like that, and you go to this number two, which is far from the first operating point, and now if whatever problem happened now clears, can you stably go back to another operating point and stay there? Look at this as, for example, a fault. A fault happens, you go to a new operating point far from your original operating point. Can you stably operate and come back to a stable operating point when the fault clears? So this is very important to know what happens to a grid-forming inverter and how it can maintain its stability. But this is a pretty well-established topic, particularly for synchronous generators. For synchronous generators, we've been looking at this problem through EAC, or equal area criteria, and this is pretty well established. So, well, what can we do now if we are going to look at transient stability of grid-forming inverters? Well, before we do that, we need to know what's the difference between the two. Well, they're very similar, first of all. Synchronous generators and grid-forming inverters, particularly if you've got a VSG, virtual synchronous generator, they're very similar in many, many areas. But there is one big difference, and that difference is that in synchronous generators, you've got very high overcurrent capability. You can easily go to 5, 6, 7 per unit, depending on your synchronous generator. When there is a fault, you don't necessarily need to limit the current. There are internal mechanisms of the synchronous generator that will limit its current, and it always stays in that voltage control mode. Well, it comes at a cost, which is fixed structure, meaning that you cannot really change it. This is what it is. This is the synchronous generator. There's almost no flexibility in terms of controllers that you can have. Their parameters are fixed, so you cannot really change things. But when you've got a grid-forming inverter, you've got very, very low overcurrent capability, depending on how you design the system. It could be 1.1, 1.2. Sometimes you might find products that are up to 2 per unit in terms of overcurrent, but that means if there is a fault happening at the point of connection of your inverter, you must limit the current. So as soon as you limit the current, you go to current control mode. In order to actually understand this, remember the control structure that I was showing. There was a current loop, voltage loop, and a primary loop. So as soon as you detect the fault, and as soon as the current that is given to the current controller from the voltage controller, that set point, is actually increasing, you have to saturate it. You have to say, okay, this is my limit. I'm unable to go beyond that because it must protect my switches of the inverter, and I'm unable to operate at any current beyond the rated value, which could be anything between 1.1 to 2 per unit, depending on the vendor. So that's a big limitation, and that's probably the biggest difference between your grid-forming inverter and your synchronous generator. But at the same time, your grid-forming inverter comes with lots of flexibility because it's like everything is like control. So you can control your inverter, you can control the controllers, you can actually manipulate the controllers that you're putting in the structure. You can change the swing equation parameters. You can actually put other mechanisms in that control structure to help your grid forming inverter to stably operate and go through the fault that is happening. And you want to make sure that you can stably operate and go through the fault. Now, how do we do that? How do we limit the current? What happens when the current limit is reached? There are a number of ways that we can do this. One of them is mode switching, which means that as soon as you detect a fault and as soon as the maximum current is reached, you immediately switch from grid forming to grid following, and you say, okay, I'm going to only operate at given current. I might activate also a PLL. And it will become a current controlled inverter. So this is possible, and it might have been implemented in certain areas, but what it means is that you won't have any voltage control anymore. The other way is to limit the references for your current. So if you remember, we had a primary controller which was feeding into a voltage controller. And then the voltage controller were feeding certain references, IDref and IQref, into a current controller. And that would then result in the actual V and Q components of the current. Now, what you can do, you can actually look at these references and also put a saturator after these references in order to protect your switches. And this is it's a typical way of protecting your switches in commercial products. Most products are actually using something like this in order to, if they are using this particular control structure, this is the more accepted way of limiting the current and making sure that you're protecting your switches. But there are different types. How can we implement this? It really depends on what you want to do. One very obvious way is just to say, okay, I'm going to protect my switches. I want to make sure that the magnitude of the current is not exceeding a given limit. So I look at the magnitude of my current. So these two are given by my voltage controller, IDref and IQref. I look at the magnitude and I just saturate the magnitude at the level that I want. That's one way. There's another way, which is called direct prioritized limiter, deprioritized limiter, which means that you give priority to ID. So IDref, you say, okay, I want the ID to have the flexibility to go between a negative Imax and a positive Imax. I don't care about my IQ. So I give priority to ID. I let ID to be even Imax. And if ID reaches Imax, obviously I set IQ to 0 because there's no room. But the priority for me would be ID. Obviously, the other way is Q prioritized. So you give priority to IQ. In that case, you're limiting your IQ between negative Imax and positive Imax. And if there is room for ID, you actually go for ID control and determine how much ID you can inject based on the maximum current. So depending on which limiter you use, you'll get obviously different performance, different dynamic performance. But there is this variable that is very important to look at, and that's the phase angle of the saturation or the phase angle of the current at the time that you're saturating it. And that depends on the saturation limit or the saturation level of your ID and IQ. Now, each type will actually affect your system differently. And the question is, which one is more effective? Which one is actually a better way of limiting the current when you're looking at a fault? To answer that, we need to go a little bit deeper and understand what happens when we are looking into a fault and when there's a fault happening in the system. You're most certainly familiar with this power angle curve. This has been used for transient stability of synchronous generators. It's essentially you're comparing your mechanical power with the electrical power, and there is an stable equilibrium point. If you have a fault, you might accelerate from there. This is the stable equilibrium point. And if you accelerate and reach this point, which is on a stable equilibrium point, and if you go here, then your system is lost and you go to the positive feedback area and you become unstable. A similar thing can be applied to grid forming inverters. Having said that, obviously we know there is a current limit which makes things different, so we need to take that into account. But essentially, a similar concept can be developed for a power angle curve can be developed for grid forming inverters in order to look into their stability. How? Let's assume that we've got this grid forming inverter and we are hoping to look at the power angle curve for that while we are subjecting this particular grid forming inverter or this VSG to a fault. If everything was staying in the in the voltage control mode, then we would have a curve like this. So similar to a grid, similar to a synchronous generator. But this is not always the case, and we know that we might have current limitation. Now, if we are in the voltage control mode, this would be the maximum deceleration region. If we are here at the stable operating point, up to here, we can decelerate. And if the fault is cleared anytime before here, we can stably go back to the point and the system will be stable. But we know that we have this current limitation. We know that as soon as the current is more than a given limit, we have to limit the current. Now, this red curve shows the power angle curve of this system when your current is limited. So when the current is limited, this inverter is injecting this much current, and this current going to the voltage at the point of connection, the voltage of the grid, will tell you how much power you're injecting, and you can come up with this red curve. This is the power angle curve for this system in the right, when the current is limited. Now, when you look at the two, your current limitation is happening here. Now that means this dashed line will be the P delta curve of a current limited VSG. Up to this point, I'm still in the voltage control. And after this point, I go to the current control, and this will be my curve. And then this dashed line will be the P delta curve of my current limited grid forming inverter. And I need to use that if I want to apply EAC to this particular scenario. And this will be my maximum deceleration region, obviously much smaller than when I have a voltage controlled or not current limited VSG. Now, if I had more phi sat, so you can actually, it can be, if you write all the equations and plot this, you'll see that your phi sat will be here. So that would be the distance between this point and pi over 2. Now, if my phi sat, or the saturation angle of the current, is larger and larger, this graph here, this current limited mode curve, will shift towards right. And I'll be having a little bit more deceleration region, meaning that if I can have a system in which my phi sat is larger and larger, or well, more negative in this case, I can have a larger deceleration region. But what does that mean? Having more phi sat here can be actually translated into having more IQ. So if I have more IQ in my system, this region will be larger and larger. What does it mean? It means that we probably, if we want to have a larger deceleration region, and if you want to increase the stability margin of our grid forming inverter when we are operating in a current limited mode, it is probably better if we go for Q prioritized current limiter. And that is typically what we try to do with grid forming inverters when we want to limit their current. Typically, we try to opt for that Q prioritized current limiter because it will help us to get more of this stability region, and the chance of coming back will be better and will be higher, and the our delta C, or the critical clearing delta, will be a little bit larger, giving us a little bit more time to come back to where we were, coming back to a stable operating point. So after establishing this, let's have a look at what happens actually if we are looking into this Q prioritized grid forming inverter. Well, if you look at this, we've established that this will be the type of P delta curve that we get in a current limited grid forming inverter, and this will be our UEP. UEP stands for unstable equilibrium point. So if this is our SEP, stable equilibrium point, so we actually traveled to here, and if the fault is not cleared at this point, obviously we go to the positive feedback region and the system becomes unstable. Here is a case study that we've done, and in here you can see, well, probably easier to see in the time domain. This is time versus delta. This is power versus delta. This is power versus delta. This is time versus delta, but this is probably easier to see. This is the omega or frequency of our inverter versus time. At this point in time, well, this point exactly, the fault has been cleared. There are two case studies here, one of them right before delta C being the delta here, so the clearing, critical clearing delta. So one of these case studies is right before and one of them is right after that delta C, based on this curve that we have developed for this particular grid forming inverter. So as you can see, one of them, the system remains stable because it's right before UEP that we are clearing the fault. One of them is right after the UEP and we're clearing the fault. So if the fault is cleared right after UEP, your system is already lost and you become unstable. But if you're before that, the system will remain stable. And that's probably normal and an obvious conclusion, because now we know that this particular grid forming inverter is entering that negative feedback region. But there's another interesting actually phenomenon happening here, and we call it the end point of this delta curve, the P delta curve. And that end point is actually has nothing to do with that P delta curve. So the P delta curve was essentially telling us whether that grid forming inverter, which is current limited, whether its P delta curve is actually remaining stable or not, and whether we go to that negative feedback region or not. But there's another point, like I said, this endpoint. And if you reach that endpoint, that will also make your system unstable. In this particular case that I'm showing here, that endpoint is here, which is already in the negative feedback region, and already you're unstable, so you don't care about it. But what if there's a scenario that we've got this endpoint here, before I reach actually this point here, which was my UEP. And if I reach that endpoint before reaching that UEP, again, my system will become unstable. What is that? So, well, look at this scenario. So in this scenario, and I'll talk about that endpoint, what it is, but this scenario, we actually have, again, a grid forming inverter, and probably this is, again, easier to see here. That the system, well, we've got a fault, and the fault actually is supposed to clear here 8.6, but we haven't reached this point yet, right? We haven't reached this point yet, but still the system is unstable. So the fault has been cleared before we reach this point, before we reach that UEP for the P delta curve, but my system is still unstable. It cannot recover. The reason is that endpoint that I was talking about is happening here before UEP. But what is this endpoint? This endpoint is essentially caused by the voltage controller that we've got within our grid forming inverter. Well, let's have a closer look. This is the this is the control structure of the grid forming inverter that we've got. We had this primary loop, a voltage loop, and current loop, and this is the Q prioritized current limiter that we have. So we looked into the voltage controller and we reformulated the voltage controller, and we came up with this particular structure in which essentially looks like a feedback system. The details of that are in a paper that I'll show in a second. And we actually realized that we can, again, reformulate the control structure in this format. And there is this reference delta, which is nothing but VG sine delta VSG minus delta G, essentially the phase difference between grid forming inverter voltage and the grid voltage. And this M is this function. Now, in a normal operation, we looked at this M and it looks like this as a function of ISQ. That ref delta is something like this. Now, if that's the case, and if we apply something similar to EAC criteria here, as far as we are operating here and we go through the fault and come back here, everything is fine and we can remain stable. But there are certain scenarios that we might actually have that delta C, which is the critical delta, that it actually gives me this reference delta. It is already larger than this M that we actually determine here. And this condition is sufficient to make this system unstable, or this voltage controller unstable. And this delta C might be essentially less than the delta critical delta C of that UEP of the P delta curve. So essentially, if I go back to the slide that I had here, this particular scenario here that is becoming, the system is becoming unstable at this point, that delta C that I'm showing here, that delta C is happening before the UEP of the P delta curve, meaning that the voltage controller is becoming unstable before my negative feedback region is achieved or is reached. So the system is becoming unstable, not because I'm going to the negative feedback region of the P delta curve, but it is becoming unstable because the voltage controller has become unstable before I even reach that. So this is very interesting to see that it's not only that P delta curve that might make your system unstable, but if you've got a Q prioritized system, there is a chance, depending on different parameters that you've got in the system, and the parameters are essentially the grid impedance as well as your Imax and different parameters that you might have in the system. And this comparison will tell you whether the system becomes unstable or not because of your voltage controller. Now, you can, using that, you can actually identify boundaries for your system. So, and compare the boundary that you get for the P delta curve and the boundary that you can get for this voltage controller, and see when your system will become unstable. Whichever is reached earlier, that determines the boundary of your system in terms of stability. And that insight can help you to actually apply certain enhancing control. And I'll very briefly touch on that at the end of the presentation, how this can be used in order to make the system more robust with respect to fault. More information about this particular phenomena can be found in this letter that was published, I think, 3 is missing here, 2023. So with that, very briefly, I'll talk about also about transient stability of a pair of grid forming and grid following inverters. And we'll see what happens if a fault is happening at the point of connection of a system where you've got a grid forming and a grid following inverter connected at one point of connection, because that's a pretty typical scenario where you would connect a grid forming inverter, a VSG, to, for example, a solar farm, and you want to support your farm, or you want to support a particular part of your network where you've got a grid following inverter and you want to help it in terms of system strength or voltage control. So what would happen if a fault happens there? So in this system, we assume that there's a VSG, a grid following inverter, and there's a common bus, and we are connecting to a SMIP case. Well, not so much SMIP here, but an infinite bus here. And we are having a line in between our point of connection and the grid. We probably won't have the time to go through all the details of this analysis, but what I want to show here is just a high-level overview of what we did, and I'll put the paper as a reference, so if you're interested, you can go and read that. But the idea was to look into the voltage at the point of connection, and we actually derived an equation for that point of connection based on the phase angle at the phase angle of the grid following inverter and the phase angle of the grid forming inverter. And it looks like something like this. So the voltage at that point is a function of your delta and theta. So it actually has this very strange shape. All the equations for that are in the paper that we published, and I put it. I have already put it in the slides, and you'll see what it is. But using this can help you to determine different boundaries for the stability of each of these grid forming and grid following inverters. If we had only a grid forming inverter, this would be what you were after, right? We already have looked into that, and we said that if we go past this stable operating point, reach this unstable one, we go to negative feedback, we become unstable. Similar concept can be applied to these surfaces that we've got here. And first, we have applied a surface here for the grid forming inverter, and we've determined the boundaries for the stability boundaries for the grid forming inverter alone. Then we looked into, okay, what's going to happen if I want to apply a similar concept to the grid following inverter, where in this plane that I've got, the grid following inverter is unstable. And then obviously combining the two, you can find what is the boundary for transient stability of this grid forming and grid following inverter together. Now, if you look at the 2D version of that, that's probably easier to see. So this area here, my grid following inverter is unstable. This is the grid forming, which is unstable. And this is where both are unstable. And this is where the pair will remain stable. So with the analysis that we did, we managed to find the boundary or the area that both of these inverters are stable at the same time. So it can help you to design your pair such that you maximize this region that both are stable. It's a little bit, of course, well, we don't have enough time to go through all the details of that, but it's in a nutshell, it very quickly can show you the boundaries of this parallel system, and it gives you like what is the stability margin, how far you are, like what is the distance between your UEP and SEP in this system. It's very intuitive. If you look at the paper, it's not difficult to come up with this boundary, and it's not difficult to come up with this distance. Make it easy to for planning or for design stage. And there's a potential to extend this to multi-IBR system, and very briefly, I'll talk about that. But if you're interested, the details are in this paper here, transient stability of parallel virtual signal generator and grid following inverter, which will tell you the exact procedure, what you should do to achieve that boundary. Now, very briefly, let's talk about multi-IBR system. What happens if you want to go to multi-IBR system and see what is what is the boundary, or what is the limit of operation there. Going back to that very simple system that we had before, if there is just one IBR, one grid forming inverter, this is the distance between your SCP and UEP. So intuitively, the larger this distance is, the better it is, right? The larger this distance between the 2 points is, it means that you've got a larger boundary for operation. It means that you have more time for your fault to be there before you become unstable. So it is useful to know for a given system how large this boundary is, and the larger this distance is, actually, it means that the more stable, well, it's not a good term to say more stable, but the larger this distance is, the higher the chance of remaining stable when a fault happens. Now, this can, we saw that this concept can be actually applied to a pair, grid forming and grid following. The larger the distance between this SCP and UEP in a pair, again, can tell you whether that pair will tolerate a longer fault or not. Now, this might be applicable actually to larger systems as well, as we already have done some studies around this, and we are trying to understand what happens in a larger system. So this is a large system that we've been looking into so far. This is a radial network where we are having a number of inverters connected to one point of connection and connected to the grid. This example actually can be, for example, a renewable energy zone. In Australia, we're having a number of renewable energy zones where a number of IBRs are being connected to the network radially. And this is a perfect example for that. So far what we've done, we managed to...
Behrooz, just in, this is very interesting, but just in the interest of time, so we can have some time for
Yeah, no, absolutely. I
questions?
think I'll be done in a 2-3 minutes, if that's
Okay,
okay.
okay,
Yeah, yeah, yeah.
yeah. In 5 minutes.
So yeah, so what we've done so far in this system, we determined where the UEP and SEP are. I'm not going to go through the details. I just want to put this slide here, and that publication is not out yet, but hopefully it will be published very soon. And you can see how you can determine the distance between UEP and SEP in a large system as well. And now we are working on mesh networks because this is radial, and we're hoping to go to a mesh network as well. So very quickly, I'll go through the last part of the presentation, which is enhancing control and how we can actually, now that we know these things about these grid-forming inverters, how we can actually make them better, how we can get more out of them. For the Q prioritized current limiter, there's a very simple trick. If you actually put the upper limit of the Q current to 0, if this one is 0 in your system, it essentially prevents you from going to that positive feedback. So with the insight that we gathered, we realized that if you put the upper one 0, and it doesn't have any impact on that extending that transient stability region when you go to current limited mode, but it can help you not to go to that positive feedback. Again, details are in this paper, very quick results that I can show here. One of them is the normal Q prioritized. This one is the normal Q prioritized, which is unstable after fault. And then this one is the one that you have activated this technique, and it remains stable. The other enhancing control that we came up with, and it came out of that pair, GFLI, GFMI pair stability analysis, was this technique of adaptive power reference control. Without going to the details of that, essentially what it does, it looks at the voltage, and when there is a voltage sag, this mechanism will be activated. And it is more or less equivalent to reducing your gain, droop gain during a voltage sag, and it can help you to maintain the stability of the system. And it's only active during the voltage sag. So it maintains the system stability even when there is no SEP. Again, details are in this paper. A very quick result I can show. So this is the system without any APRC or active power mode, active power reference control, adaptive power reference control mode. Without that, the system becomes unstable after the fault. When we activate this APRC, the system can maintain its stability even while there was not an SEP in the previous case. And this is another case study where we did, and we had a fault and also a line tripping to show that it is very robust. So this is a very simple technique, but it can help you extend your transient stability margin by far. So a summary, we looked into transient stability of grid-forming inverters, and we saw that it can be negatively impacted when you have a current limiter in the system, and you must have a current limiter because you must control current to protect your switches. And we saw that in a Q prioritized mode, we might actually have certain stability modes, not because of the EAC, not because of the negative feedback region for your power delta curve, but because of the voltage controller. And we actually look into certain tools that you can estimate the stability limit and the margin that you've got in a single grid-forming inverter, in a pair, and in a multi-IBR system, which is work in progress for us. And we looked into some, two enhancing control solutions, pretty simple, but very effective solutions that can help you extend the grid-forming stability margin. Thank you so much, and I'm hoping that I stayed within the time limit.
You did great. Thank you very much. Thanks for